So before I start, let me check whether the audio and as well as the screen is visible and audible. Any problem with the audio?
No, sir.
Okay. So today we'll be starting with the gas. Already we have started in the last class. We have dealt with few of the concepts behind the gas, classifications of different types of gas we have seen in the last class, and even some of the parameters related to gas we have seen. So we will go on the flow. So parameters will be um, get used to it when you go on solving the problems. So bit by bit. Uh, so hope everyone is having the data handbooks with you today. Okay. So this particular, I told you in the design too. So the theoretical questions are very much least in number. Most of them are in problems itself. If at all you get some of the theory questions from the GARES topic is this particular question. So this particular question has been repeated many times. This is the only theory question which I have seen in your question papers. Okay, which says derive an equation for the beam strength of a gear tooth, and this is also known as the Levy's equation. Okay, beam strength of the gear tooth, or it is also known as the Levy's equation. So this is the only this thing theoretical question which I would observe in your question paper. So kindly concentrate on this one. Today we are going to derive this particular equation. Okay, shall we start?
Yes, sir.
Okay. Let me check how many of you are active now. Just raise your hands. Let me see. Good. Good. So let us start this. So I told you there are two different wheels which turn, rotate one another. So those are known as gears, as we have discussed in the last class. The bigger one is called as a gear wheel, and the smaller one is called as a pinion, isn't it? So this one is particularly called as a gear, and the smaller one is called as a pinion. Okay. Irrespective of whether it is driving or driven. Okay. Uh, which of these two wheels, according to you, is more stressed up? I mean to say, more forces it has taken. It has taken the more load out of these two gears. So whether it is a gear wheel or whether it is a pinion, according to you, will be having a more impact or a more load content. Pinion, isn't it? Because it is small when compared to the gear well. If it is driver also, driven also, the pinion will be under the more load. So what happens? The load cycles, pinion would take the more amount of load cycles. Therefore, all the design calculations most of the time will be based on pinion. Remember this. Okay, all the calculations will be based on the pinion wheel since it is taking the more load. Okay, so in the Levy's equation, what we will do is, so okay, I have considered a pinion. Now I will just draw a pinion like this. The pinion has n number of gear tooths like this, isn't it? It has n number of gear tooths all around it. Okay, so while analyzing the Levy's equation, what we'll be doing is we will be analyzing in such a way that every tooth is a cantilever beam. For example, like this. So this particular tooth is a cantilever beam, and this particular tooth is a cantilever beam. Every tooth, it goes on for every tooth. Now, what we will do, we will take only this particular cantilever beam and analyze the things. Got it, everyone? So that is what I have drawn here. This one. Got the imagination of this thing? So every tooth would be considered as the cantilever beam. Okay, that's great. Okay. Now, let us try to analyze the various forces which acts on a gear tooth. Okay. Okay. Suppose this is a gear tooth of gear wheel, and this is a pinion tooth of a pinion wheel. Okay, so this is entirely different wheel, and this is entirely another wheel, like this, something like this. Got the imagination? Okay, so this whole sort of thing is I can say a gear wheel, and this is a pinion tooth. Okay, so now the gear is pushing the pinion, isn't it? The force is exerted from this tooth to this particular tooth, like this. So I would take a normal for both these surfaces. What I will doing is I am taking a normal for these two surfaces. Okay. So whatever the force is acting on this particular normal, I would take it as Fn. Since you know that you have studied in norm also, the forces will always act in the normal direction. Okay, so that's why the normal for both the tooth profiles, and I have drawn a normal along which the force is acting, which is known as Fn, and that particular Fn, the normal force, is this particular thing here, like this. Okay, now this particular force Fn, what I'll be doing is I will be resolving into two components. One is Fr and other one is Ft. So these are two resolved components of the normal force which is acting. Okay. So Fr is nothing but your radial component. I just write here. So Fn, you got to know that Fn is a normal force. I'll just write here. Fr is the radial component Fr is a radial component. According to you, this particular Fr is acting something like this. I would just highlight this upon like this. So this particular Fr is acting like this. And your gear wheel is all around like this, correct? And here is the center of the gear wheel. Now, according to you, this particular Fr, which is the radial component, is tensile in nature, or it is bending in nature, or it is compressive in nature. Just try to analyze the component Fr. It is acting somewhere like this, onto the gear tooth, onto the gear like this, and this whole sort of thing is your gear with a single tooth like this. Okay, what do you think? Whether it is a tensile one, or a compressive one, or it is a bending one? Compressive, very good. So I would take this particular component as the compressive component. Okay, next. Next is Ft, isn't it? Ft is this particular thing. Okay. Now, try to analyze the gear well once again, and the gear tooth. Okay, so this Ft I have marked here also. You can refer here also. The Ft is here. According to you, the Ft, which I call as tangential component, is a radial one. I mean, tangential component, whether it is tensile, bending in nature, or compressive in nature. Bending, It's clear, right? Very good, very good. So it's a bending component. Okay, understood the all three forces, the normal force, which is being resolved into radial component and a tangential component, and the nature of these forces. Any doubts until now? Any doubts, guys? No, good, 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 good. So the maximum amount of load is being exerted. You can visually say the maximum amount of load is being exerted at CB, correct? So always when a bending occurs, the maximum amount of load will be acted at the pitch point or the end point or the connecting point, isn't it? So because the length is more, bending moment increases, naturally the force at this particular point would be the maximum. So, okay, according to that, so anyone remember the bending equation, guys? Bending equation you have learned in your mom, even you have used in your design one also. The bending equation. Anyone?
MB by I is equal to sigma by C.
Exactly. M by I is equals to sigma divided by C, that in turn equal to, there is one
E
more
by
component.
G theta by
Very good. So it is E divided by R. Very good. I'm happy, man. Okay. Now, so what is M? M is a bending moment, the maximum bending moment. I is the moment of inertia. Sigma is the bending stress which is produced. And C is the distance for the outermost fiber. R is the radius of curvature. And E is the elastic modulus. All those different parameters you have already learned about it, isn't it? Now, considering these two equations, what I will do, I will just write sigma is equals to M cross C divided by I. Now I want to define moment of inertia. Okay, I want to define moment of inertia for base B and height T. How would you define it? I want to calculate moment of inertia for this particular section now. How to calculate a moment of inertia for this particular section, which is rectangle in nature.
dq by 12.
Exactly. So I is equals to moment of inertia. If I want to define for this particular rectangular section, it is BT cube divided by 12. Now, what is C? C is the distance of the neutral axis from the outermost fiber, isn't it? So it is, I would say the neutral axis would pass at the center. Now I want to define this particular thing, which is C. Can I write C to be T by 2? Correct? Half of the length of the two thickness.
yes, sir.
Correct? So I would just take C as T by 2. Okay? Now, substituting the value of C and the value of I in this particular equation number 1. Okay? Just substitute. It would be better that parallelly you solve in your notes. And that is the way it works on. Okay, you take your notes in front of you, keep solving along with me. You will be getting involved. Any doubts in solving, you can just contact me in between. Okay, it will be better. Okay, so just substitute, guys. So m into C is d by 2 whole divided by I is BTQ by 12. Now, I want to define the M. So how would I define M here? So just analyze here. This is the force acting, Ft, correct? And this is the perpendicular distance. This is the perpendicular distance, which is h. I have written as h. Okay, so how would you define the bending moment which occurs at CB? This is CB is this particular line. how to calculate a moment.
Force into distance.
So force into perpendicular distance, I would say, correct?
Yes.
So now, what is the force which is acting here?
FT, sir.
Ft is the force which is acting, and perpendicular distance. What is a perpendicular distance?
H.
H is a perpendicular distance. It's the same thing I would take here now. Okay, I would take M is equals to Ft cross H. Good. So now, can I just replace this here directly? M I would take here, and I would replace it to be Ft cross H. Now, when I solve all this, okay, so you can cancel this stuff here. 1s, 6, t goes away, 2 remains. When I rearrange this, what I would get is 6 ft h divided by bt square. So this is now sigma. I would take this particular equation as equation number 2. Everyone got this stuff? Got this particular equation?
Yes, sir.
Okay. Now, for this particular equation, I'll take another page now. Okay, what I'll be doing is, I would be extracting ft from this. Okay, just try to extract ft is equal to what it is, sigma bt square divided by 6h. Am I correct? So for this particular equation, what you do, you just multiply and divide by P. What do you mean by P? P is nothing but your pitch. So just multiply and divide by P. So what happens here? So Ft is equals to sigma Bt square divided by 6h into P divided by P again. Okay. Now, I'm just rearranging the terms now. What I would do is, I would keep sigma b p in one side and all the remaining stuff t square divided by 6hp in a bracket like this. Okay. Now, everyone have your data handbook with you right now?
Yes, sir.
Just stop here.
Yes,
What you do, open your data handbook and look at this particular page. We will get to know the terms as and when we solve more number of problems. Okay, we'll get to know the terms. Just have a look. No need to remember everything. Okay, at the initial stage of the course, no need to remember everything, and don't be in a frightened mode that if you don't know something, nothing will happen. You'll get used to it. Okay, be calm and just learn. Okay, now see, center distance is represented by A, face width is by B, CV is your velocity factor, small d1 and d2 are the pitch diameters of pinion and gear. So kindly read all the parameters which are just listed on the first page. You'll get to know about the parameters. That is my intention. Okay. So just kindly read all the parameters onto the data handbook just for a few more seconds. Okay, so we have taken P value, isn't it? So where is the P? Can you just identify here the list of parameters given in the data handbook? Can you identify P there? So P is nothing but the circular pitch according to here, isn't it? So it should be in mm. Its unit is mm. So P is nothing but the circular pitch, he says. Now, let us go further in the data handbook, page number 202. So all the parameters I have given. I told you to just remember all these parameters in the last class. Go to the another thing. Okay, the first, this thing, spur gate details he has given. So in that, many formulas, basic formulas, which was supposed to be remembered by you, it's already been given in the data handbook. In that, the first equation, it says the circular pitch. So what is the value of circular pitch here? Can anyone say me? See, here is the formula. Can I take circular pitch to be pi m? It's available in the data handbook. I hope everyone is having with you. If you don't have also, in the Google Classroom, I have just shared the soft copies, isn't it? Correct? So from this, can I take the value of pi to be pi cross m, pi into m? Can I take it from the data handbook?
Yes, sir.
Okay. So what I would do, I would take here. So P is equals to pi into m. And again, what is m? Look into the first page and get to know the things. What is m there?
Module.
It's a module, right? So just substitute the things back here. Sigma B P, okay, cross, now T square as it is, 6H. Now P, I would replace it as pi cross m. Any difficulty up till now?
No, sir.
Good. Now, I want you to search the first 2 pages of the data handbook. Yes, the first 2 pages of the data handbook, and identify this particular equation here. So, only this part. Can you find anywhere the highlighted portion in your data handbook? The expression which matches the same? Just search and tell me.
Y is equal
Yes, Sat.
to 204 page, sir.
Page number 204. Okay. This is how much? 203. And here it is 204. Correct. Where is that particular expression which I've just showed you?
Levy's equation, sir.
It's a Levy's. Yes, it's a
Y
Levy's
is equal
form
to-
factors. So here it is, right? So can I take t squared divided by 6 pi hm to be as small y, which is known as the Levy's form factor?
Yes, sir.
Yes, sir.
So same thing I will be doing here. So that is equal to sigma b p cross, what I have done is I have taken t square divided by 6h pi m to be y, which is known as Levy's form factor. From where I have taken it? I have taken from equation number. Can anyone say the equation number and the page number? What is the equation number?
12.5.
12.5 and
12.5. So page
A.
number 204.
204.
Correct. So from this I have taken this to be y. Now substituting in this, what I would get? I would get it as y. So what is the tangential component? It is sigma BP into y. And again, check this particular equation. Can you find in data handbook once again?
Yes, sir.
where it is equation number
12.5a.
12.5a, again same page number 204. So which is where it is, I just highlight. So it is somewhere here, correct? And this ends your particular derivation. Any doubts in this particular derivation, guys?
Sir, could you show the diagram, sir?
Diagram, yes, sure. Okay. Okay, no need to copy it down. Okay. Anyhow, I'll be sending this particular notes which is neatly written. But for me, I want you to solve whatever. If you're solving a derivation, just solve. Okay. Anyhow, leave the space for the diagram because it takes a lot of time so that every student finishes the diagram in the class. Leave the space for it, and definitely I would give the notes for it. But I want you to be solving the derivations and the problems along with me. Okay. Now, let us look into some of the assumptions for this. Okay. So while deriving the Lewis equation, some of the assumptions are made. Can you not just read it? The first point. Can anyone read just first point? Girish? Girish?
Yes, sir.
Read the first point there. Assumptions.
The tooth is assumed to be a simple cantilever beam.
So the tooth is assumed to be a simple cantilever beam. I have explained to you regarding this. Next one.
The tangential component of a force is uniformly distributed across
Uniformly
the
distributed
face
across
width.
the face width. So if the tooth is something like this, okay, so here it would be your face width. So all this is your face width, isn't it? And it is, he says it's not a single point load, rather it is spread across the face width uniformly like this something. Okay, so that is his point of saying. Next point, Girish.
The effect of the radial component, which produces direct compressive stress, is neglected.
So in the course of the derivation, whether I have concentrated anywhere on the radial component, only we have calculated Ft, isn't it? So the radial stress which was acting is usually neglected. The Fr, I told you, this is particular force is neglected. Next one.
The maximum stress occurs where the entire load is at tip of the tooth.
Tooth.
This is not
True because
true because more
than
one pair of the teeth will be in
teeth
contact.
in contact. So generally what happens, yes, so if there is a wheel and a pinion matching, what happens, more than 2 to 3 teeth would be in contact. So if I closely move this, what happens? So the contact point here for the first engagement is somewhere at the tip. Okay. For the second is somewhere at the top, in the between. So I cannot generalize the statement that it would be always acting at the tip of the tooth. That is what he is saying. Okay. Next one. The effect of stress concentration. Girish, complete this last point.
The effect of stress concentration and manufacturing errors are neglected.
So stress concentration affects your study in the design one, I guess, because of the notch, because of the keying, whatever you do. So there would be definitely a stress concentration. Even the gas has a stress concentration, but all those factors are not considered while deriving the Lewis equation. Even if there are manufacturing errors also, all those error ratios, compensations are not considered while deriving the equation for FT in a Lewis equation. Is that clear? So any doubts in this particular derivation? Okay, so now if all of you open your attendance sheet and mark the attendance within next 1 minute, okay?
Sir, sheet link.
Same link, no change.
Sir, link, sir.
ಲಿಂಕ್ ನೀ ಆಲ್ರೆಡಿ ನಿನ್ನ ಸೇಮ್ ನಿನ್ನ ಏನು ಶೀಟ್ ಯೂಸ್ ಮಾಡಿದ್ಯಲ್ಲ ಅದೇ ಲಿಂಕ್ ಇವತ್ತು ಕೂಡ ಓಕೆನಾ
ಎರರ್ ಬರ್ತಿದೆ
ಇಫ್ ಯು
ಸರ್.
ವಾಂಟ್
ಸೆಂಡ್ ಮಾಡಿ ಸರ್. ಸೆಂಡ್ ಮಾಡಿ ಒಮ್ಮೆ.
ಓಕೆ ಆಲ್ರೆಡಿ ನಿಮ್ಮ ಗೂಗಲ್ ಶೀಟ್ ಅಲ್ಲಿ ಸೇವ್ ಆಗಿರುತ್ತಪ್ಪ. ತಗೊಳ್ಳಿ.
Thank you, sir.
Okay. ಏನೋ ಅಸ್ವಾನ್ ಕಲರ್ ಪಿ ಹಾಕಿದ್ಯಾ?
Excuse me, sir.
Yes.
Sir, it's showing some error. Can you just cross-check, sir, whether my attendance is placed or not?
Okay. What's the name?
Sir, Amir, sir, for MT17 ME022.
17 ME022. Yes, it has been marked, right, Amir?
Okay, sir. Thank you, sir.
Okay, bye.
Thank you, sir.
Okay.
Okay, sir.
Now, how much is the count? 51. So how many are present? 51. Okay. So enjoy your Sunday. Tomorrow, okay? We'll meet up from Monday's class. Take care.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.